record this on my computer. I stopped streaming on YouTube because there is an echoing, some echoing for some reason. We are waiting for 2 more minutes and we will begin. Okay, are you ready? Timothy?
Yes, yes, I'm ready.
Good. So I think you can go ahead.
Okay. Good. Good morning, or uh, whatever the time of day is, over where you are, uh, colleagues. Today I'm going to talk uh, about the database. Me and my colleagues and I have created, listing current sheets we detected using our method. Well, first thing, I'm going to talk a little about what our method is based on. Our method uses the be our method is a formalization of the long time observer experience in detecting current sheets. We use the changes in plasma characteristic as well as in the interplanetary magnetic field to detect current sheets. As you can see on the slide, there are some key behavioral patterns when it comes to current sheet crossings. The main interest to us is the drop in the interplanetary uh, magnetic field magnitude, a rise in speed, a rise in density, and a rise in plasma beta. These are the uh, key flags we're going to be using moving on to identify the current sheets. A few words on the already existing methods. We can generally categorize them into three groups. The first one being case studies or visual analysis. Um, these methods are generally very accurate because, well, they're done by humans. But it's obvious that if we're talking about creating a database, few millions worth of cases, it's gonna take literal years, if not lifetimes, to create something of that scale just by analyzing something visually. Uh, the next group is the semi-automatic methods, which is mainly based on PVI. The problem is that the PVI shows us all of the discontinuities, whereas not all of them are actually current sheets. So this method also requires further visual inspection and a lot of work. And the last category is the already existing automatic methods, which work good for their intended purpose. The only problem being they're really computational heavy and also are based solely on the magnetic field, meaning that while it is possible to use them on a large scale, our method fares way better with large quantities of data. And about the method itself, as I already said, we are not just using the IMF characteristics, we're also using the plasma characteristic. We're using three of them. The magnitude, we're using two plasma characteristics, the plasma beta and the ratio of alpha speed to plasma speed. The way we detect uh, the corresponding spikes is by calculating the derivatives of the set characteristics, and we then proceed to maximize the correlation between the free derivatives to remove the noise. I didn't mark it down on the slide, but it is important to notice that we require uh, the magnetic field magnitude to be uh, over a certain threshold, while the other two parameters, we're fine with just one of them uh, being over the corresponding threshold. Also, here on the slide, you can see a link to our database, which is uh, open access, so you can use it in your studies. Just be sure to cite us. The link is going to be further down in the presentation as well. Now I'm going to talk about the test bench. Uh, we used CIRs, coordinate interaction regions, or rather SIRs, which are the shorter-lived cousins of CIRs to test our method. The reason for choosing SARs was because you could see, you could rather count the angular speed of an SIR and thus calculate the uh, current density. More on that later. Uh, as you can see on the slide, if you would look at the picture in the top left corner, it's actually a video which I'm going to launch right now. This is an SIR. You can see that it's a bit of a curve going from the sun to Earth to Mars currently, and we can see that it goes all the way to stereo A without breaking up, so we can get consistent consistent data for the plasma. And on the right side, you can see the plasma speed and density at ACE, which is in between Earth and Sun, and stereo A during the SIR crossing. Um, and on the bottom, you can see uh, shifted the shifted data to ACE's position in time, and it is clear that the structure of the SIR remains largely the same throughout its movement. Now let's talk about validation. Um, we calculated current density using the formula on the screen, with the magnetic constants being obscured a bit by the text, but well, I'm pretty sure that that is not some forbidden knowledge, which is readily available online if anyone is interested. Um, the current density is also a sure sign of a current sheet crossing, well, the current density being over a certain threshold. We took a 0.5 threshold for the sake of this study. And the problem again being that current density requires the angular speed of the CIR to calculate well, to calculate the current density. So The thing is, this method cannot be applied large scale as it only applies to a few structures where we can actually calculate the angular velocity. Um, but here's the comparison of the calculated current density and the uh, current sheets our method has identified and their corresponding current density. As you can see, the location of the current sheets is largely the same, especially when it comes to identifying clusters of current sheets. The correlation overall for the two SARs we used to validate was around the zero point 0.8 mark. Um, And the second method of validation we used is we actually compared our results with the Gang-Lee's method, with the vertical line showing the uh, identified current sheets at a randomly given time interval, and the correlation between our two methods was once again around zero point 0.8. Um, Gang-Lee's data spans 1 year, so we were able to compare the data for those for that year with our data, uh, and that once again goes to show uh, that our method is slightly better at large quantities of data because we already have a database spanning 12 years with more than 7 million individual current sheets identified. Um, so here you can see a beautiful graph that is a polynomially smoothed graph of the number of current sheets per day for the years starting in 1998 and in 2008. And the database itself is, again, available uh, for your use over at the web page on screen. Uh, and yeah, a few conclusions. We created a new method of the automatic identification of the current sheets in the solar wind, uh, which is a formalization of the long-term experience of the observers. The method was validated twice by comparing the current sheet locations with the current density maxima and with Gang-Lee's current sheet database. And the method can be applied for statistical analysis of the of sheet's characteristic and study of the turbulence and intermittency in the solar winds. More on that uh, is going to be said by Olga in the second part of the today's event. So be sure to catch that presentation as well. Once again on screen is the link if any of you are interested in our database, and also the citation for the article we wrote on the method. Now I'll gladly answer any questions.
Yeah, I have a question. So you said that your method is the formalization of the long-time experience of observers.
Yeah, it is.
So you use three parameters. One is the magnetic field and two plasma parameters, beta and the ratio of plasma speed and alpha speed, right?
Yes, that is true.
Is there any physical justification to say that wherever the beta jumps up or the plasma, the ratio jumps up, it is a current sheet?
Yes. Here, well, here is the slide where I talked about it. I must have been not clear enough. As you can see, there are numerous studies cited in our article on our method, and here are a few examples. The bottom left the bottom left panel shows that the plasma beta uh, has a spike in when the current sheet crossing occurs, and this is not a one-off scenario. That is something that you consistently see during current sheet crossings already identified by other methods. And same thing goes for the increase in speed and the drop in the interplanetary magnetic field magnitude.
Yeah, but this is from the observations that you see in observation that is what happens often, but we know what current sheet is, and we understand that across the current sheet, the magnetic field changes sign, the anti-parallel component. So this has some physical sense. Similarly, from why should beta jump up if there is a guide field? I don't think it will jump up. If
Well,
there is a guide.
Our method is based on the observations. You could surely use other parameters, but well,
May I comment too? Look, first of all, if you have this peak in density, look at the CS et al. This statistical analysis. If you have a sharp increase in density located exactly at the current sheet, and if at least one of the components crosses the zero line, of the magnetic field components crosses the zero line, that you will have beta increased. Most of current sheets observed in the solar wind are high beta current sheets. But of course, any automatic method can miss something. Any of them. Gangly's method and many other methods that work with the automatic identification of current sheets, they always miss something. If Timothy show just these jumps in magnetic field and other parameters, we always have a threshold also. So it's like looking for some most of current sheets strongest.
yes, the automatic method, I actually said that, is never going to be as accurate as just doing it by hand. Luckily, machines have not yet surpassed humans in every aspect. But well, the main goal of this method and the database is to identify, to catch the bulk of the current sheets, because if you have a method that misses every 10th current sheet even, and well, it still gives you 7 million current sheets to work with. That is better than not having those 7 millions and instead trying to figure out for years and years a method that's going to be 100% correct, which is it's just not going to happen because
Yeah, I understand.
yeah.
I understand that.
And another thing which is related to this, which was also mentioned by Emmanuel in chats, that's the reason that we use two characteristics while requiring only one of them to be over the threshold. That's because in some cases the plasma beta does not spike enough for us to detect it, but in most cases the alpha-n ratio to the plasma speed does reach the intended threshold. Like I said, when comparing it to the already existing methods like Gangly's, we have around a 0.8 correlation, with it going as high as 0.9 during certain periods of time. So also there is the matter of calibrating
Okay.
the method, because you might not catch some smaller current sheets if you've set the threshold too high, or you might not catch some big ones if you set the thresholds well, even higher, or you might catch some noise. So
Okay.
it's, yeah.
Yelizaveta had, excuse me, we just going out of the time. So the question from Yelizaveta, I'm pretty sure that you both can connect each other later, okay? I mean, you can be in touch, okay? Yelizaveta, you
Thank
raise
you.
your hand.
Thank you, Zaza, for interesting presentation. My question is about turbulence in the solar wind. You mentioned that you were planning to analyze turbulence in the solar wind using your database. Are you consider the current sheet like the elements of turbulence, or you mean something else?
Well, that is a great question, but I'm not going to take to go ahead and steal a part of my colleague's presentation. Like I said,
I will talk about this.
this is exactly the subject Olga is going to present about in the second half of today's event. So you'll just have to wait and find out.
Thank you.
Yes, there is my email at the bottom right of the slides in case any of you have any questions or, well, anything really. Make sure to write me. I'll be glad to receive some feedback.
It's an interesting question from Zoltan. Is there a substantial difference between the derivatives of plasma parameters and the PVI of the same plasma parameters? Look, PVI is just a method which checks for very short and very quick changes in the magnetic field. Nothing else, just not components, just magnetic field. It's included actually. In some way, it's included. It's one of the parameters. But we added two more. So this PVI method just can identify all discontinuities on the way, but we try to choose only current sheets. That's the difference. Yes, it's the correlation between PVI and, for example, the derivative of magnetic field is very high, always. It's practically the same if you look at the formula. Have you tried validation your method with simulations? Not yet, not yet, not yet. Yeah, Antonella. Antonella is here. Antonella, please speak up. I haven't seen you for ages. Antonella.
Good morning. Good morning to everyone.
Good morning, Nature, but I have joined you at the very beginning.
Yes, yeah. Antonella,
I think that PVI and derivatives are strong correlated, as you already said, but only on small scales, because the derivative respect to the time should be on very small scales, on very small lag difference in time. And in this case, indeed, PVI is strong correlated with the current that is a derivative of the magnetic field, is the curl of the magnetic field. But you have to go to small scale in order to have a better correlation.
yes, exactly. That's my point, because we have a second resolution. It's quite enough to correlate with PVI very well, but yes, it's PVI is normalized, of course, but the derivative is also something normalized, right? It's dimensionless parameter.
Yes.
So it's practically the same, but we add something more to specify the type of discontinuity. Okay, we have to go ahead. Thank you, Timothy. And the next speaker is Valentina Zharkova. We will enjoy a 25-minute talk.
Yes, hi. Let me start. Let's share the screen. It is so wonderful to have the talk before about existence of current sheet, because every time when in the past I was given this talk, I needed to persuade the current sheets exist in the heliosphere. We had this problem with Olga for ages, so I appreciate this great work you've done presenting these current sheets in the heliosphere. Here, the current sheets we see in the corona, which is yesterday seen from short presentation from Sophie with Nicole. What we had problem, I was doing this part for 20 years, and always we have problem of this thin current sheet presented in here, which we see in 2D, how it can provide this emission which we observe from flares and provide electrons about 10 to 36, 10 to 37 electrons per cubic centimeter per second. So this was the problem. Then people came up with the theory instability and occurrence of magnetic islands. And then the problem started moving on somehow. So what I will tell today covers some problems. The role of magnetic topology, timing of acceleration, interaction between electrons and ions, resolving the particle numbers. You don't need to have these huge particle numbers because you have the circuit established in between. And we speak about energy spectra, pitch angle distribution, and touch a little bit generation of turbulence, which I see everyone is now very interested. So what we look at the simulation of particle motion in 3D current sheet with X null point and then O-type null point as here, which started 2002 with PhD of Mykola Gordovsky, who works now in Manchester. But here we will use peak simulation 2.5D with XO peak code and 3D with VP code. So what basically who don't use peak, I explained that we not only use the particle motion equation, which is on the left-hand side, which follows the particle trajectories into the diffusion region, but we also evaluate the plasma feedback through Maxwell equation, the electromagnetic field induced by the same particles, and then we try to separate them. What we did, we actually fixed this original field as static. And in order to understand how particles behave, we only follow this variable magnetic field induced by Maxwell, and then we see how the particles changing and how they accelerated. At the end, I'll show that we relieve this static field. We made this together, and this is how we obtained the turbulence in 3D simulations. So what basically one thing which comes up when you start doing simulation, that main acceleration of the particle happens on the current sheet midplane in here. And that's depending on the parameters of the magnetic field topology, your protons or electrons, these are protons trajectory, we have large gyro radius, so they rotate pretty wide around the midplane. These are electrons which are trying, they accelerated much quicker, the acceleration time 10⁻⁷ seconds, protons 10⁻�3, 10⁻⁴. Therefore, electrons accelerated quicker, they try to get away, but they cannot get away, they create a cocon around the midplane, and this is seen as a top loop source in solar flares. So what we discovered that actually trajectories of protons and electrons in the same current sheet are substantially different. Despite that both accelerated in the midplane, when they get ejected, protons ejected in one semiplane, in this case it is positive X, you see this is the midplane, and this is positive X, and electrons ejected to the negative X in this particular magnetic field topology. There is a separation of electrons from protons and ions. Also, the particle gain more energy closer to X null point and much less energy further from X null point, which naturally lead to power law distribution in the energy spectra, which was shown by Zharkova-Gordovsky 204 Astrophysical Journal, and 2 papers on the power spectra 205 Manras and Space Science Review. What we found, though, that this happens simultaneously. So on the right-hand side, we simulated with Agapitov the motion of electron, which shows very thin layer where electrons are accelerated. So if they enter the current sheet at the point z equals 0, they will be ejected at the point between 200 and 400 meters. But look what happened with the protons on the left-hand side. They enter the same point, but they will be accelerated at the 4,000 meters, about 10 times longer. So it explains you why these electrons, when they're ejected, they probably cannot go far away if they ejected too close to axial point. These protons with their electrostatic charge will return them back, creating this loop-top source. So again, these thin layer, at that time we did the test particle approach and look at the simulation Karimabadi et al. In peak, and this initiated for us to do particle in cell simulations with Siversky when we got grants. So what we basically, when we did simulations, when you put plasma density into the current sheet, in this case 10 to 6 particles per cubic centimeter. So with the blue side, we show these are electrons and red are protons. So you see that it doesn't matter from which side protons enter, they always are ejected to the negative semiplane, and doesn't matter which side electrons enter, they always are ejected to the positive semiplane. So having these numbers of particles, so we, in the previous simulations, we use about 10 million of particles, but with here we used much larger number of particles, about 10 to 10. So you can always have energy distributions for protons, for electrons, which you see the distribution has 2 maxima for each kind of particle. So if this beam is ejected, it has 1 energy for the lower energy, 1 energy for the high energy. So this is, and we also can evaluate pitch angle distribution depending on the magnetic field direction. So to here summarize, so what is happening with magnetic field topology? Your particles enter, are dragged in by magnetic diffusion into the midplane x equals 0. So the protons, electrons dragged from both sides, but they are assigned by this magnetic topology to be ejected, in this case, protons to the negative semiplane and electron to the positive. So depending where the proton come, if proton come from the same side where it will be ejected, it will gain a little bit less energy, this lower line, this less energy, it's called bounce proton because it bounced from the midplane. The protons which come from the opposite side to which it will be ejected, it's called transit proton. It gains energy while it reaches the midplane, and it's called transit proton. So obviously it gains higher energy, but because protons gain much less energy than electrons, it is not obvious if you look at transit and bounce electrons. So you see the transit electrons gain subrelativistic energies, about sometimes a half or third of speed of light velocities, while bounce electrons, they can reach midplane. In this case, for lower density for the heliosphere, the bounce electron cannot even reach midplane. So what is the consequence of this? So we have 2 issues here. We have separations of electrons and protons, and we have split of the particle of the same charge into transit and bounce, which have different maxima in energy and different, obviously, pitch angles. So the separation, what separation leads? So we evaluated with Agapitov in 2009 that potential between separated protons and electrons exceeds the original electric field, reconnection electric field, which accelerate these particles by 10 150 times in this case. So basically, the particles, separation of particle induce very strong so-called polarization electric field across the current sheet. And it is not it is not the reconnection current, reconnection electric field, which is perpendicular to the screen. So electric reconnection field is perpendicular to the screen, but this polarization field is in the screen across the X null point. So it looks like this. On the right-hand side, on the top, here is polarization electric field depending on the ratio of components. And for very weak BY component like shown in here, the profile of polarization electric field look like this. And we compare this profile with the profile of ion velocity distribution when they were crossing heliospheric current sheet, which follows very closely profile of polarization electric field induced by particles in this heliospheric current sheet. It was very encouraging. So obviously, this polarization field can have any shape and it reflects magnetic field topology. So what I'm saying that magnetic field topology is very important factor in acceleration of particles because magnetic field acts as the catalysator. It keeps the particles inside the magnetic field topology until particle reaches the critical energy and can break from it. What also it shows that, remember this separation and those electrons which in low density plasma and low magnetic field cannot reach midplane. This is exactly what was observed very often when the crossing heliospheric current sheet, that the pitch angle distribution has turned by 180 degrees at some distance from the current sheet midplane, from the heliospheric current sheet. And people could not understand. While now, when we know the topology of particle acceleration, we know clearly that this is because these bounce electrons cannot reach midplane, and we see them. And distance at which the bounce electrons are turned is actually proportional to the guiding field magnitude we evaluated in that paper with Olga in 2012, shown here. What we done further with Kian Shah in the US Air Force project, we use the same phase field. This is the zero guiding field, so we don't have any separation, the first line. The second line guiding field is weak, or 0.1 of the main magnetic field. This is a strong guiding field, which is equal to the main magnetic field BZ. And this, all the current sheet here, length 1 gyro radius of protons, and this bottom current sheet is the thickness of 10 gyro radius of protons. So we here present the pitch angle distribution for low or transit or bounce electrons and high or transit electrons. So you see that even in the case of absence or very low guiding field, pitch angle distribution of these particles are different. But the more the guiding field is increased, you can see that with the increased guiding field 1, we have very strong, very well directed beam, electron beam in this location, which for the high energy transit particles, while the particles bounce, remember they have this like big medallion type distribution. They started from 0 and then come to 180, return back. The protons, they don't have this notion as pitch angle distribution. They follow because they're pretty heavy particles, but the ejection from the current sheet are in the diagonal. So from negative, it is ejected to the left bottom hand side, to the positive, it is right top hand side. Although when you start increasing the guiding field, when your protons are assigned by separation to be ejected to some path, the protons become ejected to the path to which they assigned by the given magnetic field topology. So this is very important thing because it also imposes, you see, the separation imposes different pitch angle distribution on the transit and bounce particles of the same charge, which gives you very strong indication how to look and to analyze the data when you obtain from observations. So here's example. I presented this pitch angle distribution for low bounce and high transit particles with the observations 24th of June 2004. And here is the passing the current sheet. And you see with nice strolls, which we observe in here, strong energetic particle in high energy channel of pitch angle distribution. While if you more look to the lower energy distribution, you see the distribution more diffuse, like we presented here. And of course, everything was said before was about single axonal point. But we know from observations and the simulation, as soon as you allow to have some disturbance during the simulation of current sheet, and you can obtain immediately magnetic reconnection with magnetic islands. So here we run 3D peak simulations with VPeak. In this case, we did not separate static and electromagnetic field. We decided to see how the reconnection current sheet will develop. So after time 32 omega ion gyro frequency -1, we got formed very nice two large magnetic islands with the axonal point between them. So on the left-hand side, these are the density, here the energy of the particles. And for this particular occasion, so we have now taken into account particle acceleration in the island. Magnetic island is a natural presence in reconnecting current sheet. So what we do in the paper, we considered on the left top corner, here are two islands which are merging to each other. We call them coalescent islands. They move towards each other. And here there are two squashed islands. So we evaluated the polarization electric field. It turned out coalescent island, it's positive, it's increased, while in squashed island, it is positive, it is increased, like was in axonal point. But in coalescent island, sometimes because they squashed to each other, the polarization electric field become actually negative. It plays against particle accelerations, which is very important, that sometimes you don't see accelerated particle when islands are merging. So how acceleration happens in island? It mostly happens for electrons. They run around the island near its shells, mostly, and basically electrons can be accelerated in a single squashed island to relativistic energy. So this resolves the particle number, because particles can be very effectively, very quickly accelerated, and they accelerated basically from one axonal point to another. So this quasi-Fermi acceleration, they pick up energy axonal point, get reflected into the island, reach another axonal point, again reflected. So this is what our coalescent island, the density distribution on the left-hand side for electrons and the protons look like. So if we make open boundary on the island from this side, you see that the particles become ejected. In this case, protons are ejected to the positive semiplane, and electrons are ejected to the negative semiplane. So the same, what we were saying about separation, valid for magnetic islands. The only thing for coalescent island, that this polarization field works against acceleration and can be decelerating particles, which probably often is observed. So polarization electric field doesn't, not necessarily every time works in coalescent island. If you compare coalescent island, the top and the bottom is squashed island. So squashed island, when the ratio of the vertical size to the horizontal size is smaller, so vertical size is smaller, it turns out that They're much more effective accelerators. And that what is happening in Squash Island, we can effectively accelerate protons, which are accelerated actually close at the Squash Island axis, like here, which shown on the bottom plots. Again, here the electrons accelerated, here the protons for Squash Island, they got high energies and they get ejected as expected. The energy distribution of particle accelerated in the islands are also power law distribution, although they're in this particular configuration, the power law was about 4.2, and the Squashed Island had slightly harder distribution than Coalescent Island because they have much more energetic particles. So this what results, whether you have single axonal point or multiple null points with axonal point, you still have acceleration of particle, and this acceleration happens still within these axonal points, either like Fermi type or like normal drift acceleration. What is important that now having this simulation with particle in cell approach, we can simulate pitch angle distribution. So we can assign that your observer satellite is crossing along this green light. And here we can present how your high energy or transit electron pitch angles and the low energy or bounce electron on the bottom plot look like. Here is practically not present guardian field. If you add the guardian field, you see that the high energy distribution, they split into the two particular beam for from each side from the mid plane, while the lower energy parts become very diffuse. And this is what we observed, what reported Olga in her paper 2020, the observation with the stereo of the pitch angle distribution of electrons here on this side, which shows that high energy distribution show this change of pitch angle in here, as we expected, while low energy distribution show this diffusive distribution, like here with the more dense, with this direction where the particles should be ejected. So we can look at another event. In this case, we thought the observer was crossing path was just at the head of the magnetic island. In this case, your high energy electrons show very small variation around the 180 degree, similar like we have here when we have the island, while the lower energy electrons, bounce electrons, show this ring type of pitch angle distribution, which we observe kind of here. So basically now we probably have power to try to emulate the observations by applying different angles in the simulated data. And recently we published in this 2021 here in Zharkova and we published an interpretation of Parker probe observations shown in here. Again, this is the high energy electron with the two straws, high energy beams coming from the current sheet, and lower energy electron looking like as diffusive as possible, which if you look at this picture, these are your straws coming from the current sheet for high energy electron, and this is your nice lower energy bounce electrons coming here, while another observation when the current sheet was a bit wider corresponds more to the right hand side, when the high energy electrons shows only in one direction when the beams are separated, while lower energy electrons show this double change like in here, 0 and 180 degree. You cannot invent it. It was observed and we just simulated. So obviously it shows that bounce and the transit electron actually impose very important signatures on pitch angle distributions. So these are things we finished about pitch angle distributions. And now most recent, we just struggling to get it published because we only started, but we done kinetic turbulence generation. So remember that we have distribution bounce electron, transit electron have bump in tail distribution. And sometimes this bump is the same height as the main distribution. So what it causes, two-beam instability, Bunemann instability. We published in 2020 this electric and magnetic field. So we found that variations of electric field much more visible, while magnetic field variations 10⁻⁷, basically you cannot observe them. But these are turbulent, which generated near X null point by two electron beams. This is what's shown. And it shows very nicely that how many different waves and turbulence were generated. So we decided to investigate. This was published in 2009 with Seversky and Zharkova. We evaluated that for the flaring event, these turbulence corresponds to Langmuir waves with the wavelengths about 2 meters, which probably later cascade to some other waves. Then with He and Zharkova, we presented this turbulence. We didn't evaluate it. We left it for the next paper, which I'm trying to present you here. So I return back to this fully 3D simulations with PIC. And what we do, the turbulence does not appear the first two rows. It starts appearing in this third row, but it's fully developed only in the fourth row. So basically, turbulence do not appear immediately. You need to have these particles accelerated and form these bump in tail distribution before the turbulence can be generated. And what kind of turbulence we generate? So we present here turbulent magnetic field and turbulent electric field.
Valentina, 2 minutes, okay?
Okay, we needed that. So it gives you the slope minus 2.7 near ion inertial length. And this is presentation in wave numbers. Then we looked at the turbulence in the particular points in this simulation. So this is my magnetic island in the point X null point C, in the point close to the start of the island, and inside the island, point A. And here we do the cutoff. So if you put perpendicular plane, this is perpendicular plane, how electrons behave in the point A. These are ions. Remember, ions sitting in the midplane of the magnetic island. And here is electron, which are getting ready to get on the shell of the magnetic island. What has happened that magnetic electric electrons have a electron hole in here, basically in this point, very important. How it is affected, they create still turbulence. And the turbulence we evaluated first with wavelet power. What we found that we have high frequency turbulence like we had, not only Langmuir, we have a number of high frequency turbulence shown in here. This is high frequency turbulence, especially seen in the points C and B in here, in the perpendicular electric and magnetic field, which are basically assigned normally either to Langmuir, but it could be Bernstein waves, because you see, remember when electrons are ejected, they are moving across the magnetic field, which is creating the Bernstein waves. At the same time, we also have some small variations in the lower hybrid frequency, but this is happening in the point A, which is inside the magnetic island, which lower hybrid frequency, this is lower oscillations, which are also seen very nicely this lower hybrid frequency waves, which probably can be assigned very often Whistler wave or oblique Whistler waves, perpendicular. So these are particular locations where oblique Whistler waves can be formed by instability of two beams. Remember the proton beam, if you come back here, this is the proton beam. It has split into number of different filaments. It is Kelvin-Helmholtz instability for the for this kind of plasma, and this instability causes formation of this lower frequency turbulence close to the lower hybrid frequency. And this is basically it. What I can conclude that magnetic field topology imposes very strong signatures on the particles. Particles telling you where they come from and how they go through. So if you know where to look, you can obviously extract from the particle, from the pitch angle distribution, not only from energy spectra. Energy spectra are most summarized. You can get them from summary effect anywhere, but from pitch angle distribution, we can see where the transitive bounce particle come and how particle can be accelerated. We can evaluate whether the particles came through coalescent island or squashed islands and evaluate from their parts which part of island they come through. And what we see is that even turbulence, which is generated inside the current sheet, basically is imposed by the topology and reconnection electric field, which accelerate particles to particular configuration and produces the turbulence we observe. Thank you.
Thank you, Valentina. One quick question.
Yes?
Okay, no, not from me. One quick question. Any questions?
Can I? I'm Francesco
Sure.
Pecora. I have a curiosity rather than a question. Maybe I missed something. When you spoke about the first peak model, you told that, or I understood that the fields that act on particles have been fixed to some constant or predetermined values. And
yeah, they're given electric magnetic field. You can assign them, or you can take them from MHD simulations.
Yeah, but in this case, it becomes a sort of test particle simulation rather than a.
No, it is peak simulation, because after that you allow them to relax. So we add these fields. We only keep it from the start separated, but then we start adding this field and they affect how they're doing. But what we're following how particles behave and where all these characteristics come from. They come from the particles, because at some stage I think it was one of the group from Dalton. They said, oh yeah, we got parallel electric field. They discovered parallel electric field during these simulations. It was not parallel electric field. It was accelerated electrons, which were ejected from the current sheet and moving along the largest component of magnetic field. So basically, they discovered accelerated electrons. So this is what I was saying. You can describe the problem either through magnetic field, but much more beneficial was described through the particles, where you figure out when the physics come from. So only when you follow the particles, we managed to discover that we have all these distributions caused by the particles. We have pitch angle distribution caused by different bounce and transit particles. And then, in order to restore the full picture, we simulated 3D. We forgot about this static. We allow current sheet develop its own reconnection and simulated it, but we knew that what the particle will do in this model, and this will help us to understand where we can build in this perpendicular plane to the current sheet mid-plane and see how the particles behave, how they were accelerated.
Yeah, I understand the particle physics is very important. My question was more on the model. If the electric field and the magnetic field that you're saying, that you're writing here on the left are the same, or those with the twiddle?
No, these are the same, but they are added with this one. So we added them on every step. Simply we remember to which part we add whatever happens on the right-hand side. So we, for ourselves, we knew which part is from the static one and which part come from, you read this paper, Zharkova, Siversky and Zharkova in here.
Okay, thank you so much. Thank
Journal
you so much.
Plasma Physics 75. This is well described.
Okay.
Thank you.
You're
Great.
welcome.
Thank you. Sophie, you're the next. Thank you, Valentina. Thank you.
You're welcome.
Hello.
Hello, Sophie.
Let me share my screen. Can you see it?
Yes, yes.
Okay, great. Okay, and I have the pointer. So yeah. Good afternoon, everybody. I'm presenting here presentation that we prepared with Nicole, who could not attend. And I will be presenting observational support for acceleration processes linked to magnetic reconnection in solar flares. So I will focus really about what's happening in the low corona. And I will present a few recent observations. Of course, I cannot cover everything, but I picked a few that are of interest for me. So what can we do observationally to study particle acceleration and magnetic reconnection? We can use the different diagnostics that we have. And we have here an example of recent observation of a solar flare. In grayscale, you can see the EUV emission that is emitted by hot plasma. And we see a loop, dense loop, and also structures that is a plasma sheet, but also we believe carries the current sheet for the reconnection process. And it's extended high, even after, even higher than what we see here in this image. And on top of that, we have microwave emissions and X-ray emission. And those are signatures of accelerated electrons. The X-ray emission is a Bremsstrahlung emission. And the intensity of this X-ray emission is proportional to the ambient plasma density. Therefore, it's usually more intense in dense plasma in the loop, or even better at the foot point of the loop here. The flare was on the limb, partially occulted, so we don't have any foot point emission. And that's actually why we can see maybe more clearly what's happening in the corona for the X-ray. And the color things here is the microwave emission at different frequencies. So it's between 3 and 18 gigahertz. And this is gyron synchrotron emission produced by the electrons as they are propagating in the magnetic field. And the frequencies depends on the magnetic field strength, on the density of the plasma, the density of the energetic electrons. So this is a very powerful tool to study what's happening here for the electrons. And recently, in the recent last years, we've been able to do both X-ray and radio imaging spectroscopy. So here I only show images, but we also have access to the energy distribution of those emissions, and that's what we use to really understand the distributions of energetic electrons. And of course, the EUV images, as the one as is shown here, is really important to understand as the geometry of the event. That's how we can identify such plasma sheets. And we can also see motions of plasma in EUV. I will talk a bit more about that later. And finally, a note is that magnetic field is really difficult to measure in the corona, but the microwave emission, because it's sensitive to the magnetic field, can be used to calculate the strength of the magnetic field at the emission sites. So what can we learn from that? We can really look at what the magnetic connection process is doing for the particles. And there are many different scenarios that are possible in solar flares to accelerate particles. The common assumption is that reconnection happens somewhere in this plasma sheet or current sheet. And of course, if there is a current sheet, there are direct magnetic electric fields that can accelerate particles. We also have usually reconnection flows or reconnection jets. So the plasma is ejected on both sides of the reconnection site. And in particular for the downflow, they can be, as they reach the dense material, the dense loop below, they can be the reason for the creation of a termination shock. And such a shock is also a good place to accelerate particles. This also is a good place to create plasma turbulence, and turbulence is of course a good way to accelerate particles as well, but this is something I will not cover so much in this talk. So the big questions here are to understand how and where the particle acceleration occurs during solar flare, and how that can constrain our understanding of particle acceleration in that context. I wanted to start by talking about the magnetic field and current and electric current measurements that we can do in the solar atmosphere. As I said, it's very difficult to do in the corona, and what we can do is measure the magnetic field in the photosphere, so at the surface of the sun. And this is done using spectropolarimetry. This is an example of observation of magnetic field in grayscale here. And because we can have, we have the whole vector magnetic field, we also can calculate the current density, which is represented as blue and orange dot here. These are the places where we have enhanced electric currents at the surface. And a few years ago, I've been working on comparing those electric currents, the localization, with X-ray sources, which are the signatures of energetic electrons. Of course, here I show an example where everything is on disk, but you have to realize that we are comparing things that are not exactly at the same altitude. So we can look at this schematics of what's happening. We have the measurements in the photosphere, and they are linked to magnetic field that extend in the corona that I have drawn here to schematic, the magnetic field in green. We think that there are current sheets in the corona where this is emitted, and so where we have the magnetic reconnection, and so we are comparing this with X-ray emission that can be emitted in the corona or in the food points. What was shown in this study is that there is a link between the location, but also the dynamics of X-ray emission source from energetic electrons and the photospheric electric currents that are the traces of what's happening up there and traces of current sheets. And so that's an indication in favor of acceleration in link to this current sheet structure. This also was confirmed by a statistical study of the same kind of observations by Timofey et al. Recently. Of course, looking at photospheric measurements is not ideal because everything we really are interested about is happening in the corona. And there has been also work on showing that moving to measurements at the chromospheric level is a better way to look at things. Here we have an example of change that are seen in the current density at photospheric and chromospheric level, and compared to X-ray emission again. So those are the faint contours here. And we see that there is a better correlation when we use the chromospheric magnetic field, which makes sense. And so this is something that I think will be very useful to look at again with, for example, decreased observations in the future when we have more measurements of chromospheric magnetic field and electrical density. But we have other ways to also look at magnetic field in the corona and try to understand the electric field in the corona. Those are from observations of the gyrosynchrotron emission that I mentioned before. And we have here an example of a flare for which here in grayscale, we still have the EUV data and we still see a current sheet. And this is the associated gyrosynchrotron emission. And all of these points here correspond to a different spectra that are shown here. So in this study from Shen et al., it's really demonstrating the capability of radio instruments such as IOPSA for this observation to do spectral imaging spectroscopy and provide the spectra at different points in the corona. And since this emission is sensitive to the magnetic field strength, we can use them to deduce the strength of the magnetic field along this current sheet. And so that's what the authors have been doing. And you have here different profiles along the current sheet. We have a profile of magnetic field with height. We have also a calculation of what the electric field is. Here you have the distribution of electron energy with height, and again in here the density of relativistic electrons. And so what's interesting here is that in the magnetic field, we can see what the null point is. And at the null point where probably magnetic reconnection is happening, we have a depletion in energetic electrons. There are less energetic electrons here than below. So that might be maybe because there is not much acceleration happening there, or that might be because the electrons don't stay there and there is a fast escape of that region, from that region. But the other thing is that we have here the Y point, which is the top of the arcade of loops that can be seen in EUV. This is where also we have the hard X-ray emission, so from energetic electrons. And this is first a place where the magnetic field is a bit lower. And this is a place where we have more energetic particles. And that might be because these magnetic field structures is actually trapping the particles. And maybe it's trapping energetic particles enough to produce the emission, or maybe there is also acceleration happening here at this point. This point is a location where some models predict that there is a generation of turbulence or generation of termination shock, for example. So it's a likely place for particle acceleration. Another study from Yu et al., also recent study, is completed this kind of diagnostics with an analysis of the plasma flows that we can see. So in EUV, I have here a successive images, different images in EUV where we see plasma flows and we see both upflows and downflows. And so those are marked in blue and red respectively. And if you do a time distance analysis, you can really identify all those upflows and downflows. And this has been marked, they have been marked here. And most of them originate from a single point. And that's how the authors here identify the X point where the magnetic reconnection is likely to occur. But what's also very interesting here is that each of these downflow, when they reach the region of the cusp where we have the dense loop, correspond in time exactly at enhancement of the gyrosynchrotron emission. And okay, it's not moving. Okay, yeah. The interpretation for that is schematized here, and we have a 2D view and then a 3D sort of view. In 2D, so we have this X point happening, the reconnection current on the connection current sheet, we have plasma upflows and downflows, and when we reach the cusp region, we have maybe a termination shock, and maybe additional acceleration or acceleration just at the shock, which creates the X-ray source that we see. And so, yeah, it's not very visible, but we have the X-ray contours see here, and also the gyrosynchrotron emission. And the reason why, if I can go back, we have this altitude of X points changing over time might be because we are looking at a 3D structure where these X points are at different altitude on these different loops. Alternatively, of course, we could have acceleration as the X point and have electrons that are escaping that region very fast and are trapped here. That would also explain the additional excess of emission in X-ray and gyrosynchrotron emission here. But we have other supporting observations for termination shocks, and I just want to mention a few of them here. Study from Shen et al. Looked at the radio and X-ray emission of a looped-up source in a flare a few years ago, and showed that the centroid of the radio emission sites were really stationary for some time and located exactly at the top of the X-ray source in the corona. And this was interpreted as energetic electrons that were accelerated at a shock. This is a more additional explanation for this. The scenario is quite always similar to what I've been describing so far, but we have the reconnection current sheet, the outflows in EUV, and termination shock that is in radio with these centroids, and correspond to and provide energetic electrons that then generate the X-ray looped up source. And this is something that has been matching some simulation of shocks that have been done in MHD, as MHD simulations. Another way to look at shocks is to really look at the downflows that we see in EUV. And one way to do that, on top of just looking at images that we have, we can also look at spectroscopic measurements. So to do this, this was a study using IRIS, which provides spectral information in the corona and during this solar flare. And so we have an example here of profiles seen by IRIS, where we have both a blue shift and a red shift in the line profile. And the positions of the red shift and blue shift were located at the top of this loop arcade that we can see in EUV. And they were also associated to non-thermal X-ray emission at the same location on top of the loop, which is quite unusual to see, since usually we see this emission in the footprints. So this was seen actually in the late phase of the flare. You can see here at the beginning of the flare, the X-ray emission that are seen in red and blue. We have red food points, so high energy food points as we expect. But later in the flare, this emission is really coming from the top of the loop. And this is where we think the termination shock is developing, because this is also the time where we see the blue shift and red shift in the iris data. So this was explained by the fact that we probably see this arcade from an angle from which the flows that are after the shock are deflected on both sides of the arcade. And so that's why we see blue shift and red shift, because some of it is coming our way and some of it is going the other way.
Sophie, just 1-2 minutes, okay?
Okay, yeah. Yeah, and so just as a side note, this is something that have been also of course studies in simulations. We have here an example of a 2D MHD simulation where a termination shock is created, and then particles are injected and accelerated in that configuration. And they've shown that this magnetic configuration is creating kind of a magnetic bottle where the particles are trapped. And again, that would explain why we see the X-ray emission on the top of the loop. So I've been presenting so far a lot of things about termination shock and particle acceleration happening below the reconnection site. But we have to keep in mind that for some events, we know that there is a very good correlation between X-ray emitting electrons low in the corona and energetic electrons that are measured in situ that have escaped the site. And so this suggests that there is a common acceleration site and acceleration process for both of those populations. So this is a paper from Krücker et al. From a few years ago that shows this correlation, but similar results have been recently found with stereo data and presented during EGU this year. And they are also often associated with coronal jets or filament eruptions. We see jets here associated with X-ray emission for one of the events presented in this paper, and a more recent one when we also see radio emission from escaping electron beams associated with a jet. So in that scenario, it's interesting to point out that we really need a common site of acceleration for both the particles that are accelerated up and both in the particles that stay in the corona. So we may have different geometries. For jets, we usually have a standard model of interchange reconnection where we have reconnection between hot loop and open magnetic field. Recently, people are also looking at magnetic reconnection in fan-spine configurations, where we have, and here we have an example where a filament eruption is provoking different stages of reconnections, and explaining how we can have both the X-ray and X-ray emitting and escaping electrons linked to the same reconnection site. So yes, briefly, the conclusions are that X-ray and microwave imaging spectroscopy is providing a detailed diagnostic of energetic electrons and magnetic field in the low corona. And we have observations that provide, that agrees with the fact that electrons can be accelerated below the reconnection site at termination shock, or maybe also by turbulence there. But we also have, on the other hand, observations of particles that show this correlation between what's the particles that are escaping and the particles that are staying in the low corona. And so we have a diversity of configurations to look at an acceleration process at the same time to explore. And current observational diagnostics are really helping to distinguish between all of those. And I will end here and be glad to take any question.
Thank you, Sophie. Please, questions? Valentina commented. Valentina, you wanted? Okay, Elizaveta and Valentina. Valentina was the first.
Yes, I wish to point out, you reported these electrons on one of the slides, which are not moving on the loop top source. And if you listen to my talk, what I was saying, when protons keep accelerated along the midplane, they still stay on the midplane. Electrons already reach the critical energy. They try to escape. They go escape, but they can't escape far, either escape to the loop or so they keep coming back. This is why they create kind of a cocoon on the top of the loop. And this cocoon is your loop top source. This is what
yes, but this is really, so is it due, to my understanding, it's really due to the configuration of the magnetic field, or is it also due to the acceleration process itself?
It is due to acceleration process, but magnetic field, it conserves. So it is the frame which doesn't allow the particle to leave this topology and keep accelerating. The longer particle sits in this topology, the further it is accelerated.
Exactly.
So basically, magnetic field is like a catalyst. It keeps particle until they accelerated. So the longer it contain the particle inside, the higher energy it will gain. So those particles which are on the edge of the current sheet, when they do not spend much, they don't gain much energy. Those which are close to your X null point, they stay there for a long while. This is why they earn much more energy. And it turned out that when the particles are ejected, it's nice for them to be ejected into the loop leg, and go away. But if they are close to the X null point and loop top source, it means that they cannot go away from the electrostatic field induced by protons, which are still gyrating around this midplane, try to gain the energy, because magnetic topology does not allow them to go over them. And only when protons gain this enough energy, these protons will be ejected in one of those loops, either with electron or without. But these are protons which are returning those electrons and create this nice cocoon, which you observe. But you don't see protons because the energy is not, or the density probably not high enough to observe any collisions with them. You need to have chromosphere to see any ion emission or whatever.
Yeah,
So
it's more difficult to observe.
It's been published, so simply you can add to your explanation, because you don't necessarily need termination shock. It's enough acceleration in the current sheet.
But because I think the problem that, okay, if I take this one, for example, is that electrons that don't stay at this X point, right? They are mostly seen below. So
yeah, in this case, but
yes, yeah. So
in this
it depends.
case, this is a very strange case, because you have such a strong magnetic field. With the magnetic field 500 Gauss, you cannot accelerate particle. We've done simulations. Run any test code for 500 Gauss, your particles maybe will have a couple of twice of thermal energy gains, not more. So this is, I understand that you get magnetic field from where? From microwave emission, yeah? Did you?
Yes, so this is from the microwave emission in black, and this is from the extrapolation in red, and this is for, and the blue line is from another analytical model.
So I wouldn't trust completely with this magnetic field. Probably have a plus minus 200 Gauss plus minus, because even with 100 Gauss, you can't accelerate much. In order to accelerate particles to keV's energy, you have to have pretty low magnetic field. And even 100 Gauss would be too much. So it has to be lower, 50, 10. So this is what you do, doesn't fit what you observe in particles. but as some first step of evaluation, you can use it, but I would put large error bars, just people would know, no, this is not, because people who did simulation of acceleration, they know it's not doable. It's not doable.
Valentina, excuse me, we have two more raised hands.
Fine, I'm fine.
And Philippa.
If you have questions, send me email, Sophie. I'm really delighted to see that people, especially Nicole, investigate current sheets, because when we were in the RESI group 10 years ago and before, they didn't want to look at the reconnection size. So now it's a big change. Congratulations. Well done.
Okay. Elizaveta was
I have very simple question, Sophie. This question: have you real proofs that before the connection, this investigated region have the laminar structure? It's a principal question for all reconnection models and reconnection observations. It's necessary to have a laminar structure, and after that it's possible to analyze such situation like reconnection. Have you proved that this is laminar? Because your observation have large fluctuations there, I see.
Yes, I am not sure exactly.
You're not sure that this situation take place in connection with this problem.
I'm not sure I understand the question completely.
Laminar structure, and it's necessary to have laminar structure to have reconnection. If you have not laminar turbulent structure, it may be something else.
Okay, I'm not sure how this can be checked, because I assume this is really small scales.
Due to observations, you analyze a lot of works. Is it possible to state that the structure is laminar?
I'm not sure that we can. I'm not sure that we can say for sure. I think here the approach is really from the EUV, for example, EUV flows, we can pinpoint where the reconnection sites are happening, but I'm not sure we can really look into the very small scale detail that are below our instrument resolution, for example, to see that.
Yeah. You have limitations with resolution, but you have your model in analogy with magnetospheric tail. Magnetospheric tail, it's very, very turbulent. And it's integrated a lot of satellites. So we have a problem which is necessary to solve jointly in the solar flare and in the magnetosphere.
Yes.
That's why
I agree. I agree that's another possibility. Yeah.
Ladies, I have to stop this discussion because we are 15 minutes late. So Philippa, are you here? I have seen Philippa. Oh yes, please apologize. I apologize for this delay, but you see the discussion is really interesting. Thank you, Sophie.
Yeah. Thank you.
Thank you.
Okay, we can see my screen. Yeah.
Yes.
Yeah. Yeah, so that was a nice talk by Sophie, and as in the official session, I think it was quite nice for me that we had her talk just before, because some of the themes are quite similar. So yeah, I'll try and keep my talk quite short so people maybe get a chance to have some lunch. So this is a talk led by Mykola Godowski, who I think is in the audience, and it was a collaboration between Manchester and Nagoya with the addition of Ed Contar. And I have to say that sadly our co-author Grisha Vekstein passed away due to the COVID virus maybe a couple of months ago. So in some sense this talk is sort of dedicated to his memory. But obviously he had important contributions to this work. So I think we've already heard quite a bit about energetic particles in solar flares. and that actually recent estimates, the numbers are maybe even larger. This picture is not as nice as the one Sophie showed, but this is a sort of very conceptual flare with some kind of energy release, some particles, electrons escaping into space, some impinging on the chromosphere where they emit hard X-rays. And we're trying to understand more about this process. And as we've already heard, the electrons can be detected both through the hard X-rays and gyrosynchrotron emission. Some may also go out into space where they may produce plasma emission as well in the radio range. And of course, the ions also have been mentioned, but harder to detect, as we know. So that's the sort of basic picture. Of course, modelling this coming from a theoretical point of view is pretty challenging. And one of the reasons why it's challenging is the huge range of length scales involved. So on the one hand, you've got the global magnetic geometry, which may have scales sort of 10 to the 7, 10 to 8 meters, and that's very nicely modelled by MHD. The sort of fluid approximation applies. But on the other hand, we've got processes, reconnection and whatever going on within current sheets. And so we, in principle, have to consider kinetic scales down even to the, probably the smallest scale would be the electron gyro radius. And there's obviously different ways of doing this. Kinetic simulation, such as PIC, are obviously powerful tools. And we've heard nice work from Valentina about this. But obviously they can't account for the large scale geometry, the magnetic topology, and that's really essential for a flare to account for this large scale field. So one approach, it also has its limitations, but it's also a powerful approach, is to use test particles. And these have been quite widely used to study particle acceleration in reconnection. Quite often focusing on sort of fairly generic idealized models of sort of X points current sheets in 2D, 3D. And this is just really a small subset of the possible references on this work. So if your work isn't mentioned, note I did say EG, and there are many other papers that I could have mentioned. So we have done obviously some work, quite a bit of work in the past using this approach and combining MHD simulations with test particles. And quite a lot of our work over the last few years has focused on what I would call generic flare modeling, which is taking a sort of more idealized model, which captures some of the aspects of flares, but doesn't refer to any flare sort of in particular. And the model we have focused on for that is taking a bipolar magnetic region and sort of twisting up a bundle of field lines, creating a twisted loop, which goes unstable and generates fragmented current sheets. And so we start with an MHD model, we build up free energy until there's some kind of instability generating reconnection. So from MHD, we can predict the thermal emission as we obviously model the velocity and the magnetic field, also the temperature and density, the MHD variables. But we then add test particles, in principle protons and electrons. But in terms of the emission, the main thing is the electrons are giving non-thermal emission, which we can also predict. So it's this combination of MHD, test particles and forward modeling gives us quite a powerful picture. So just to say a little bit more about the test particle modeling that we do, obviously test particle model has an assumption that you have a small population of non-thermal particles and the effect of their motion on the background fields is neglected. So that is a limitation, but I said there are other advantages. So we generally calculate test particles using the GCA code, which was written by Mikola some years ago. And obviously the assumption of this is we average over the rapid gyro rotation, which we always have strong fields, so that's fine. We solve the relativistic guiding center equations for both protons and electrons. And importantly, we don't just model, as it were, individual trajectories, but we start with a statistically representative distribution, which follows the density and a Maxwellian temperature. And in this, we can take time-dependent 2D, but here we take 3D MHD fields E and B, and we interpolate those fields in time and space to the particle location. So that means our particle distribution is sort of evolving as the E and B evolve. So we can see how the particle distribution evolves. And unlike quite a lot of other work, we use at least a physically motivated localized anomalous resistivity based on the current, but also on the condition of sort of ion acoustic turbulence generating resistivity. So there, just in case anyone likes looking at equations, these are the relativistic guiding center of equations that we solve, which can be found in Northrop. This is sort of a compendium of results really for our twisted loop models, I say our generic models. So this from Pinto et al. Shows us the field going kink unstable and the synthesized thermal emission. On the right here, you can see a series of stills of the magnetic field, the current density showing the fragmentation of the currents, which gives us our effective particle acceleration. Again, the thermal emission. And then for the same model, this shows us microwave intensity and polarization and a hard X-ray source at one of the foot points, expanding, intensifying and expanding in time. So this is a sort of summary of the things we've looked at, both for say soft X-ray, EUV emission, also hard X-rays, both spatial and temporal variations. We also looked at non-thermal line broadening, considering turbulent flows, and microwave intensity and polarization. But I now want to move on from that to modeling instead of generic events, if you like, an actual flare. And so this is some work on modeling an individual solar flare, which is published recently in AppJ. And if you want more details, you can look there. So here is the event showing the EUV from AIA, the magnetic field, the sunspots on the photosphere, and the H-alpha, showing you the H-alpha brightenings. So this was an X-class flare, September 2017. There was a series of flares, but I think this is the first one. And as you can see, it's quite a complex magnetic structure. We'll see it a bit more in a moment. But you've got basically two clusters of sunspots and different regions of opposite polarity. So our modeling approach was to start with the magnetic field from a nonlinear force-free extrapolations using a vector magnetogram, then to put this into an MHD simulation, and this has been published by Inoue et al. And then what we added to this is basically a test particle approach. So we calculated the electric field from the currents in the MHD simulation, and then looked at ions and electrons and calculated their precipitation and also forward modeled the hard X-rays. So this is a kind of summary of what we do. So I'll then tell you a bit more about the details. So the methodology, in some sense, similar to what I described for the generic models, but we start with this nonlinear force-free field. There is some triggering, which then leads into the MHD simulation. We then add in the particles using the GCA approach, code that I mentioned earlier, and in some sense similar approach to what we did for our generic modeling, and then predict observables. Focus here on hard X-rays, but in principle, we could predict other observables as we did for the generic models. So here is the MHD equations as they were solved in the Inoue paper. This model assumes constant resistivity and viscosity and zero beta, which is quite a good approximation, zero beta, quite a good approximation. We then use the current from this code to calculate the electric field from Ohm's law. But in order to realistically look at particle acceleration, we use an anomalous resistivity based on the local current and the density, as we described in earlier work. So here's our sort of anomalous resistivity model. So this, first of all, shows you the magnetic evolution. Obviously, on the base, you can see the magnetic field at the photosphere and the overall evolution of the field as simulated. And you can see sort of various restructuring going on. If we shall show this now just as a series of stills going over a series of times. So this is the initial state. What is now put in here, we're now focusing, I should say, on the region sort of down here in the middle. So we're homing in on the region in the center here. And we are also highlighting in red the regions where the acceleration is happening. So the regions of strong electric field. So you can see the turquoisey field lines, or what you call that cyan, are the field lines which pass through the acceleration region. So you can see the acceleration sort of builds up and then gradually decays away. The field restructures itself in a fairly complicated way and eventually settles down towards the end of the event. And just to highlight, this is sort of basically the same time shot as there, so you can see it a bit better. This is a sort of blow up of the acceleration region at 80 seconds, which is when most of the acceleration is happening. This is a cartoon showing you the restructuring of the field, and it is obviously just a cartoon, but it's trying to simplify what was in the simulations. And so you can see the sheared arcade, which is present initially, sort of collapses down, becomes much less sheared, and we get some more field lines generated from this region of, one polarity to the region of opposite polarity up here. So quite a significant restructuring of the magnetic field. That, as you might expect, gives you a reduction in magnetic energy and conversely an increase in kinetic energy sort of associated with the reconnection activity. If we focus in on the acceleration region, we calculate first, this shows the current, the resistivity, which basically gives us our main acceleration region. And you can see the parallel velocity and the perpendicular velocity sort of associated with reconnection, sort of inflows and outflows. So now what happens to the particles? This shows us spectra of electrons and protons. What's happened? Oh yeah, there they go. They are moving in time. So you can see we start with a thermal spectrum, and then at some point in time we get this quite strong non-thermal tail developing, and then it settles down again. The number of electrons accelerated up over 10 keV is about 6 times 10 to the 36 electrons. This shows you, and we'll come to this more in a moment, the magnetic field configuration of where these accelerated electrons are mainly propagating down to the surface. So the little movie shows us just tracking down electrons till they hit the surface, and it's a sort of visualization showing you where these electrons hit the surface. You can see mainly near this neutral line here, but also in a location down here and in a few other places as well in this sort of complex magnetic topology. And we then therefore calculate the precipitation. This is at a series of times of electrons shown in blue and protons in red. Once we've calculated the electron precipitation, we can then calculate, forward model the hard X-rays, which are shown here. And we can see we have generally 2 strong hard X-ray sources associated with these regions of electron precipitation, and a weaker sort of double source associated with these electrons precipitating down here. So there was RESI data for this flare, and we find RESI showed 2 hard X-ray sources which correspond very nicely to this one and this one. There's no sign from Vesey of this weaker source down here. Maybe it was too weak for Vesey to observe. Maybe these electrons are somehow, dissipated in some other way. But basically, very good agreement here. And I should say the duration of this hard X-ray burst is mainly from about 80 to 100 seconds, although obviously it carries on sort of a little bit for longer, and that is consistent with what's observed. Valentina mentioned to me after my talk in the official session about her work with co-workers on the helioseismology of this event. And as I said, we did mention this actually in the paper. And we actually looked briefly at the connection between our results and the helioseismic sources that Valentina and co-workers found. And we found that 3 of the sources are actually very close to our sites of particle precipitation. So if we go back to our precipitation map, again, there's the electrons and the particular, I think, yeah, I'm trying to remember which ones they are now. But anyway, one of the helioseismic sources is close to the site of main electron precipitation. I think that's this one. But you can see we've also got these sites where there's significant proton precipitation, and these are associated with the possible sites of the helioseismic sources. So that's quite interesting. So just ions have got a role there. So what are we doing now? We're carrying on this work, but intending to look at more events. At the moment, we're just looking at a couple. And these have been chosen to have a much more open field. And so we can look at the escape of particles into the heliosphere. In the model we discovered before, hardly any particles get out into the heliosphere because it's a very sort of enclosed magnetic configuration. But you can see these events have got a much more mixed topology with a mixture of open field and closed field. So we should be able to consider both the impact of particles on the chromosphere, but also the escape of particles into the heliosphere. These are just shots from very early in these simulations, so there's not yet much to say about the reconnection, but this is just the beginning. And we are also now doing simulations with LAIR, which we previously used, which means we can put anomalous resistivity into the MHD model and also finite beta as well. So we will have, in some sense, more realistic MHD simulations, which is an advance on what we've done before. So that's the summary. I think rather than me reading through that, I'll just leave that, and that will allow us maybe time for questions and hopefully time to get lunch as well. So I'll stop there. Thanks.
Thank you, Philippa. Very interesting questions. Valentina wants to ask something, definitely.
Oh, no, I'm delighted what they've done. We work like together, independently, but together, which is really nice. What I just wanted to say, this, not the top source had X-ray, it was seismic source 1, but the second one, it was the first time we seen the sunquake with this second bounce. So we have not only the first bounce of acoustic waves we see as ripples, we managed to detect even second bounce, which was much slower. First time in 20 years we done it. So it is really very unique flare. And because it was at the minimum of solar activity, the atmosphere was not very turbulent. We managed to detect the second bounce. So it is a unique.
Yeah,
so.
I think there's quite a lot could be done in future more with working. To be honest, I think we came across your work on the helioseismology just at the point when we were, this paper was being, as it were, finished off. So the comparison was a, a fairly last minute thing because, we already had our draft of the paper and then we added in that, which I think is very interesting. But obviously in future, putting together maybe, helioseismology studies and the test particle models, there's a lot of potential, I think, for that.
Indeed. And we can involve our Japanese collaborators.
Because we're both collaborating with the same people.
I am afraid to go to Japan on my own, but if I go,
yeah, we were supposed to be going. We had a visit planned to Japan April last year, and of course that was cancelled. And who knows when we'll be able to go? But there we go. Yep.
I spent three weeks there on my own, and I was so lonely that I need someone to go to there together. I don't want to go on my own. Anyway, thanks.
Thank you very much. Well, no more questions? Then we proceed to the next talk. Patricio, please. Thanks.
Hello, everyone.
Hello.
Can you see my screen?
Yes.
Okay. So today I'm going to give the extended version of the presentation that I gave in the EU session yesterday about the relation of between turbulence and reconnection. I'm going to mainly focus on the electron kinetic effects, and in particular the electron acceleration due to magnetic reconnection in turbulence. So first, let me introduce and motivate this topic. As you probably all know very well, magnetic reconnection and turbulence are processes that are very closely related. On the one hand, magnetic reconnection is characterized by conversion of magnetic energy into kinetic energy. That kinetic energy can be either bulk flows, plasma heating, or non-thermal particle acceleration. In this talk, I'm going to focus on the third form of kinetic energy. Magnetic reconnection, another consequence is that it can generate turbulence via secondary instabilities. As you can see here in this, in the bottom right panel here, there is a 3D simulation of magnetic reconnection showing the development of a turbulence due to this, due to secondary instabilities and flux ropes. The left panel that I forgot to mention here is just a standard picture of a magnetic reconnection. The magnetic field reconnect and the plasma flows go in the perpendicular direction to the inflow direction. And in contrast to the previous slide, a turbulence can also lead to magnetic reconnection through current sheets. In the left panel here, I show relatively old simulation already from the 80s. This was a magneto-hydrodynamic simulation of turbulence, decaying turbulence, showing already the formation of current sheets. Those current sheets were formed at very large scale, so the thinning process is mainly controlled due to numerical dissipation or numerical resistivity. But we know from both spacecraft observations in the solar wind or in the Earth's magnetospheres that turbulence, the properties of turbulence are different depending upon the scales. The magneto-hydrodynamic scales to which those simulations correspond are very large scale, which are represented here with a typical spectral index of minus 1.7. This plot shows solar wind turbulence spectra. At ion scale, the feature of turbulence changes and is characterized by steepening of this spectral index. This indicates the presence of ion kinetic effects. This has been studied relatively quite a lot by hybrid simulation and spacecraft observation, let's say in the last 20 or so years. But the challenge now is to understand what is the role of electron effects in this process. Electron effects are really hard to, they are really a challenge, not only for a spacecraft observation due to the limited time resolution, but also for numerical simulations, because they require to resolve the smallest kinetic scales, as well as the large scale where the energy is injected into the system. And why is that important? Because turbulence can be observed everywhere in our in the collisionless plasmas of the solar system. For example, here there is a picture of the scheme of the heliospheric current sheet that sometimes can show ripples and magnetic islands. Small scale magnetic islands where there is a possibility for a local particle acceleration. Here, for example, we can see a spacecraft observation of merging magnetic island. Each small scale magnetic island is represented by a different number here. And those, these represent magnetic field density and bulk flows speed. And those magnetic islands are usually associated by an enhancement of energetic energization of electrons, as shown in the bottom panel here, that shows the pitch angle distribution of two channels of this instrument as a spacecraft. Okay, so that is the motivation of our work. Now, how are we going to tackle this problem? We're going to use simulations, two kinds of simulations. One are fully kinetic particle in cell code, which solves the standard, the full system of Maxwell equation plus the Vlasov equation for both electrons and ions. And on the right panel, there is a very short description of the other numerical approach that we use. That is a hybrid kinetic model with inertial electrons. This is really important to assess the electron kinetic effects. This code contains the whole ion kinetic effects because ions are considered as particles, but also all the electron fluid effects. So the combination of those two codes are ideal to assess the importance of possible kinetic electron instabilities on any acceleration process. The numerical setup is just simple two-dimensional decaying turbulence with an out-of-plane background magnetic field. So the perpendicular scales are on the simulation plane. We initialize the system also in a very standard way with uncorrelated alphenic fluctuations of velocity and magnetic field, injecting those waves at the largest possible scales in this system. We use a very reduced mass ratio. Those are just the first simulation for this case. We're going to improve this in the near future, as well as a relatively low plasma beta of 0.1. So, and what can we observe with this? Well, with both codes, both fully kinetic and hybrid with inertial electron codes, we observe formation of electron scale current sheets embedded in ion scale current sheets, which are much broader. We observe a similar, at least order of magnitude similar, current sheet width, or at least for the fully kinetic cases, they are mostly around 2 electron skin depths or near half ion skin depths. Both codes show a relatively good agreement of the peak values, as we can see here, of the out-of-plane current density. This shows just snapshot and the peak time of the evolution of the RMS values of the current density for both fully kinetic code and hybrid kinetic codes. This panel here shows the evolution of the RMS values with a small difference that we are still trying to understand the origin, but this possibly has to do with the dissipation mechanism or the enhanced dissipation in the hybrid code due to also possible numerical effects which are absent in the fully kinetic code, as well as the influence of waves. The waves that are present in both systems are different. And we observe also some tendency to disrupt current sheet formation due to some waves that are present in the fully kinetic approach or simulation, but absent in the hybrid model. And as for the hybrid current sheet simulation and the properties of their properties and the role of shear flow instabilities, please refer to this talk and slide by Neeraj Jain. Now, how can we assess electrokinetic effects in those simulations? Well, first, we use also kind of standard a metric to quantify the non-gyrotropy of the electron pressure tensor. This is not fully kinetic, but this allows us to characterize the locations which are more likely to result in non-Maxwellian distribution functions. We use the method by Aunay et al. 2013 here. And this correlates very well with the current sheet locations. And this plot here shows the temperature. This is just a pure thermal temperature. And that is also correlated very well with the location of the current sheet. And this shows a zoom-in region of this small square or rectangle here of the current density. This shows an elongated current sheet and some small magnetic islands. So when we look at the microstructure of those regions in the velocity space, we found mostly field-aligned double peak distribution function with long plateaus, as we can see here in those distribution functions taking near of one of those X points and near the boundary of one magnetic island, small magnetic island. This is at the X point, and this is on the boundary of one magnetic island. The red line here shows the direction of the magnetic field. So those are mostly field-aligned structures. Because of the strong magnetic field, those distribution functions are very much gyrotropic on the perpendicular direction. That is on the simulation plane. But because this is a 2D simulation, those distributions that would be unstable on a fully 3D configuration are stable in this case. And the in-plane component is relatively small. It's not large enough to trigger those instabilities. The right panel simply shows the structure, the phase space structure in the out of plane direction, X and Y in the neighborhood of those distribution functions. That shows how those reduced one-dimensional distribution function varies dependence of the X or Y direction. And finally, what are the consequences of this for a particle acceleration? In general, we found relatively very weak signature of particle acceleration. By weak signatures, I mean relatively almost no formation of power loss in the energy spectra, as we can see here. This shows mostly as this can be fit by just a thermal distribution. This was taken in the neighborhood of this reconnecting current sheet. This indicates mostly parallel heating. And this plot here shows the Fermi acceleration term due to the curved magnetic fields. And in general, the order of magnitude of this term, the contribution of this term to the total acceleration is 1 order of magnitude smaller than a parallel acceleration. But this parallel acceleration mostly leads to thermal heating. And finally, the conclusion, well, collisionless decay in turbulence leads to formation of current sheet with similar general properties in both fully kinetic and hybrid with electron inertia plasma model. There are some differences between the simulation with different plasma models which are not completely understood yet. But in such a way, we can assess the role of electron kinetic effects as well as waves. Distribution functions, we found mostly field-aligned double peak distribution, which are typical from strong guide field reconnection, but no signature of micro instability. This system behaves very much fluid-like, as well as very weak signatures of particle acceleration, which possible has to do with the strong guide field regime of this particular simulation. And that is, thank you very much for your attention. Any question, comment?
Thank you, Patricio. Questions? Very interesting. Leo.
Yes, I have a question. Very interesting talk. Regarding the micro instabilities that you refer. Now, of course, there are conditions for instabilities. For example, if you are talking about a beam and like in a double peak that is similar to a core beam, then it has to be a superalphenic beam to be unstable. So the question is whether the parameters of the instability are met. And that's something you can check.
Yes, in general, no, because the direction does not match. I mean, those beams are not in the on plane, on the simulation plane, but rather on the out of plane direction.
So that is a serious shortcoming of such a model. Because you cannot reproduce the kinetic instabilities since you're lacking the K parallel. Only maybe some projection of that.
And the projection is very small. I took into account that, the projection is very small. Yeah.
Right. So to alleviate that, you can either maybe you can do the other plane, model in the other plane, where the guide field is in the plane. However, then you cannot really model turbulence fully.
Exactly, that is the problem.
And then
hardly.
Yeah. So really, you have to do a 3D model. That's
exactly. Actually, that is the next challenge for this work in general.
Okay. All right. Good. That's good that you agree, because this 2D model misses a very important part of the physics of the micro instabilities.
Yes.
Anyway, thank you.
Welcome. You're welcome.
Some questions? Any questions? I have a comment, maybe, or question. Look, you are talking about weak particle acceleration. Actually, it was shown by Will Matthews in 1984, something like that, for the similar simulations, and it came like a surprise. And the point is, if you add some compression from one side, the acceleration will be just like boom. You will see this. We see this from observations. If you have just a field of magnetic islands, field of current sheets, just ordinary turbulence, yes, acceleration is not very big. But if you put everything inside kind of teapot with borders formed by current sheets, which additionally produce some turbulence and reconnection, etc., and press at least from one side, everything just begin to bloom.
Yeah.
Right. This is the idea of what to do with these nice simulations. Because
that is a very good idea to force. You mean to force forcing turbulence. That is one, and the other, the compression in general of current sheets due to external structure. I also observed that in different kind of simulations, 3D simulation of reconnection, where the X point of one current sheet was compressed by the magnetic island of a different current sheet. And in that particular simulation, I could observe a very efficient particle acceleration that was mainly due to that effect. So that is, I also,
that's great, because nobody actually has considered this seriously in the SoloWind for the SoloWind parameters. So it would be great if you could do this. Thank you. Thank you. The next talk will be given by Roman Kislov. Thank you.
Hello. You can
Share your
see.
screen.
Full screen. Hello. We have studied whether is stream interaction region a wave or a stream of particles. High-speed flows from coronal holes are separated from the surrounding solar wind by stream or rotating interaction region. As Sun rotates, stream interaction regions along with high-speed flows propagate in the heliosphere. A stream interaction region can be considered as a single large-scale object resembling a magnetic tube with walls of varying thickness, as you can see it, in the figure. In this case, we can think not only about the speed of the plasma flow inside these walls, but also about its large-scale movement around the sun. It can rotate. Stream interaction regions are formed in the young solar wind at the edge of high-speed flows from coronal holes. They are bounded by forward and reverse shocks, which may be not formed, of course, at 1 AU. And earlier rotation speed of stream interaction regions has been estimated on difference of moments of crossings of direct and return shock waves. It may be differ from the average rotational speed at large spatial scales. You can see some examples of illustrations from such works. Many people focus on structure of stream interaction regions. This is the subject of both observational studies and many numerical models, and you can see some example from well-known models by Lee with forward and reverse shock. And at the same time, the answer to the following questions remain unclear. Is a stream interaction region a flow of particle or a wave? Stream interaction region is typically considered as transition region between the flow of plasma from coronal hole and the surrounding solar wind. In other words, it's treated as a material object rotating with the sun. On the one hand, coronal hole particles are observed in stream interaction region. The presence of some connection between stream interaction regions and a coronal hole is obvious. On the other hand, the wave can also be associated with coronal hole. The propagation of the wave and the plasma flow are not the same things. It's known that the solar wind does not rotate with the sun at large helio distances. Also, the interplanetary magnetic field does it. And the last one is important because Parker's spiral links a stream interaction region and a coronal hole. And as I mentioned, a stream interaction region is often seen as a region between two shock waves that rotates with the sun. And finally, existing publications do not answer the question, what is this stream interaction region? Is this a flow or a wave? To answer this question, we firstly find the angular speed of stream interaction region. Here, large-scale angular speed of a stream interaction region can be calculated at excuse me. It can be calculated as the time difference of arrivals of stream interaction region front to two satellites. In our case, it's ACE near the Earth, you can see it, and stereo A is the second satellite. And you see two figure with two moments of these crossings. between these dates, which you can see, we have estimated the angular speed of the stream interaction region on one astronomical unit is approximately equal this value. That corresponds to angular speed more than on the majority of latitudes of the Sun. This is of course expected since the stream interaction region associated with coronal holes which can rotate faster than the surrounding plasma near the Sun. It's important that the angular speed of stream interaction region at one astronomical unit corresponds to tangential speed 500 kilometers per second. It's too much. It's much faster than rotation of the solar wind. To compare in the stream interaction region, the typical tangential speed of the plasma is about 20 or 30 kilometers per second. It's much lesser than 500 kilometers per second, as you can see at this figure. That is the stream interaction region and the plasma in it have absolutely different tangential speed. Next, it's a principal question. Does stream interaction region rotate with the Sun as a material object? The answer is no. Many studies have shown that the rotation is broken near the elephant surface near the Sun. Beyond the surface, the angular speed of plasma decreases according to inverse square law. There are many corresponding estimates of the angular speed. You can see two estimates here. One estimate is analytical, and the second is based on a numerical model. Excuse me. And you can see that these angular speeds are small. You see that you know that Alfvénic speed in the solar wind is much lesser than radius component of the solar wind speed, and this value is also much lesser. Thus, we can conclude that the stream interaction region is not a plasma stream because its motion in tangential direction is absolutely not the same as the motion of plasma particles. A similar situation was in the early 20th century in galactic astronomy. The spiral arms of galaxies were thought to consist of fixed set of stars, and they rotate like the spokes of a wheel. Further, it was shown that the angular speed of stars depends on the distance to the center of galaxy. Then the arms of the galaxy would be wrapped around its center like a thread on a spool, as you can see here, some concentric rounds. And then the arms of galaxies will be, excuse me, it's turned out that arms of galaxies can be described as spiral density waves. And now here you can see as result of one of many models which treated on it. Using this analogy with galaxies, we have considered a stream interaction region as a spiral wave of the density, the velocity, and the magnetic field. We can describe the motion of the plasma using standard equation of magnetic hydrodynamics. You can see it here, and we can suppose that the rotation of magnetic field is the main source of all disturbances. Then you can choose a system of reference in which all the values are stationary. All values have this form in the system of reference. They do not depend on time. And then we can move to inertial system of reference. The wave number in this system of reference can depend on time, as you can see, and all disturbances have more complicated formula with time dependencies. It's well-known results which was used in many famous works. And we assume that angular speed omega is the angular speed of the sun, because the sun is main source of rotating magnetic field in the heliosphere. And the solution of our equations for the plasma density is shown here. The axis of rotation of the sun is directed to us at this movie. You can see the rotating spiral waves. They do not contradict to observations, and you see something like the stream interaction region. And to conclude, further than the Alfvén radius, stream interaction regions rather represent density waves than flows of particles. It's a small but important result. Thank you for your attention.
Thank you, Roman. Any questions? No questions. Then we proceed to the last talk of the session, Alexander Khokhlachev. Thank you, Roman.
Thank you.
Hello, everyone. So you can see it, yes?
Please. Okay, we can see it.
Hello, everyone. My name is Alexander Khokhlachev. I'm a PhD student from Space Research Institute of the Russian Academy of Science. This study is concerned about dynamics of helium abundance in magnetic clouds. First of all, some general information. Helium is the second abundant ion component of the solar wind. The non-stationarity and inhomogeneity of the solar corona leads to formation of different large-scale solar wind structures in which the relative helium abundance can differ significantly. The maximum relative helium abundance is usually observed in the interplanetary coronal mass ejection and can exceed 10%. The relative helium abundance can dynamically vary inside large-scale structures, which can be the result of local processes in plasma. The main objective of this research were firstly study the dependencies of the relative helium abundance on some plasma and magnetic field parameters in both type of interplanetary coronal mass ejection, and secondly, study the medium scale change in the helium abundance inside the magnetic clouds and compression region in front of them. The classification of large-scale solar wind structures used in the study is based on Omni2 database and the catalog of large-scale solar wind phenomena of Space Research Institute. It includes heliospheric current sheet, slow and high speed streams, two types of interplanetary coronal mass ejector, magnetic clouds and injector, and three types of compressed plasma regions, corrotation interacting region and sheaths before fast coronal mass ejection. The differences between the two types of coronal mass ejection are rather conditional. Magnetic clouds have a high rotation magnetic field, while ejector don't have regular structural field. The upper figures on the slide show the average helium abundance in different wind structures. The red lines show values for different solar cycles. The lines of other colors reflect a comparison of the helium abundance in different phases of cycles. The averaging was done over a long time, so the highest value were not smoothed out. The lower histograms show the distribution of the relative helium abundance in slow streams, magnetic clouds, injector, and sheets. It can be seen that media values of the helium abundance in magnetic clouds and sheet are higher than in other structures. In addition, the probability that the helium abundance will exceed 5% increased significantly for magnetic clouds and compression region before them. In general, gallium reflects well the large-scale dynamics of solar wind, and it also reflects small-scale dynamics. In a recent study, Yamalaev et al. Analyzed the average profile of helium abundance using superposed epoch method. The figures on the left show the result of that work. It was shown that in magnetic cloud an anticorrelation of the relative helium abundance and magnetic plasma parameter beta is observed. Since the beta parameter is the ratio of the thermal and magnetic pressure, this fact has been interpreted as an indication that the current enriched with helium ions exists inside the coronal mass injection in the middle area. The scheme on the right shows the general view of cross-section in magnetic cloud, in which shown that middle area. The differences in the level of anticorrelation between magnetic clouds and ejecta were explained by the fact that when the spacecraft crossed an ejecta, it passed farther from the axis of the coronal mass ejection and particularly doesn't register the current. Thereafter, we proceed the data to obtain the average time profiles of these parameters. In this study, a comparison was made for the parameters taken directly from the database without any averaging. The figures show the dependencies of the helium abundance on plasma parameter beta, magnetic field magnitude, and thermal pressure for two types of coronal mass injection: magnetic cloud on the upper panels and injector on the lower ones. The black line shows the approximation. As can be seen in both types of coronal mass injection, the helium abundance anticorrelates with the beta parameter, which confirms the result of previously mentioned work. This anticorrelation is associated principally with correlation of helium abundance with the magnetic field. The dependence of the helium abundance on the thermal pressure decreases slightly for magnetic clouds and increases for ejecta. Since the selection of coronal mass ejection for magnetic cloud and ejecta is largely determined by the distance on the spacecraft trajectory from the ejection axis, these types of dependence may be due to the fact that the external part of ejection may be more affected by interaction with the surrounding plasma. This slide shows similar histograms for proton density and temperature. By definition, the relative content of helium is inversely proportional to the proton density, and the dependence is obviously decreasing. The helium abundance increases with increasing temperature. To study the correlation between parameters, an approximation was carried out by a power function. To access the quality of approximation, we used parameter which is calculated from the number of points and the correlation coefficient. The approximation reliability for each dependence was more than 95%. In first part, study of the study affects only the general trend in the behavior of the parameters and their relationship. But the spread is very large, and the next step is local consideration of the detailed change in the parameters within the magnetic clouds with specific example. To study the medium-scale dynamics of helium abundance and its behavior with other parameters, we considered the timescale of these parameters. We examined the interval from 13 April 10 p.m. to 15 April 2 p.m. of 2013. This interval included magnetic cloud and shift before it. The figure on the slide shows time series of the considered parameters: helium abundance, magnitude of magnetic field, plasma parameter beta, proton density, velocity, and temperature. The boundary of the magnetic cloud is clearly visible. The helium abundance rises sharply at the boundary and remains increased in comparison with sheath. You can also see the regularity of the magnetic field in magnetic cloud. In addition to the time series of the parameters, the bottom panel of the figure shows the time series of the local correlation. This is correlation between two parameters, which is calculated for separate 2-hour intervals. Analysis of the behavior of this correlation make it possible to distinguish the medium-scale structures. In the figure, the tendency of the anticorrelation in helium abundance and beta parameters can be seen for magnetic cloud, which confirm the result of the first part of the study. But there are also areas with both negative and positive correlation between these parameters. This slide shows similar figure for magnetic field magnitude and thermal pressure. The positive correlation of helium abundance with magnetic field is clearly seen for magnetic cloud, but for the full time interval, including sheath region, the anticorrelation with thermal pressure is more significant. Magnetic cloud has many fine structures with the positive correlation of helium abundance and magnetic field. In sheath, the structures with correlation with thermal pressure and anticorrelation with magnetic field is observed. For the full time interval, the clear anticorrelation of helium abundance and with proton density and temperature is observed, but the helium abundance in the magnetic cloud almost doesn't correlate with the proton density or temperature. In sheath, local areas with positive correlation of helium abundance with proton density and temperature are observed. In study, we also considered the spatial variation of the helium abundance by comparing measurement and at spectrum and wind spacecraft. An analysis of this correlation coefficient between time series of measurement make it possible to relieve local inhomogeneities in the plasma and in particular determine their properties in magnetic cloud. Local correlation coefficient varies greatly over time. If structure doesn't change during the transition from the one spacecraft to another, as in first region, the local coefficient is high. If shape of structure has changed, the values of the correlation coefficient is average as in third region. If structure is observed at only one spacecraft, as in region 2, the correlation coefficient is low. The maximum values of the correlation coefficient are observed in magnetic cloud and sheath before it, which indicate that local plasma inhomogeneities are not typical for these structures and more common, for example, in the slow streams. Let me summarize the results. We considered that an increase in relative helium abundance is observed with a decrease in the plasma beta parameter in the coronal mass ejection and showed that this dependence is associated with the clear correlation between the helium abundance and magnitude of the interplanetary magnetic field. In magnetic cloud at the medium scale, the dependencies of the relative helium abundance on other plasma and magnetic field parameters can be very significantly and require further research. Multiply structure in which the helium abundance correlate with magnetic field are characterized for magnetic clouds. In schist structures with correlation with thermal pressure and anti-correlation with magnetic pressure can be distinguished. Is it also shown that local inhomogeneities of helium abundance in plasma are not typical for magnetic clouds and schist before it? Thank you for your attention. If you have any question, I will try to answer them.
Thank you, Alexander. It was very interesting, and I will tell you why after the questions from the audience. Please, any questions? Well, then, no questions, really. Then I can comment, maybe. It's not a question, it's just something that my conclusions about your work. It's very important because what it shows first, then, okay, we know that schist and extreme interaction regions, they are very, very much alike. But what people try to show, usually they try to show that the abundances of helium, these values, they are determined by the solar source always. What you see in your observations, in your statistics, is practically something about the local structures. For example, it's well known that the number of alpha particles decreases significantly around the heliospheric current sheet. It's well known. And people have always thought that this feature is something relating to the heliospheric current sheet only. Practically what you see is that then if a number of current sheets increases, I will show this in my talk in the next session. If the number of current sheet increases, beta increases, and you have this correlation, number of particles of alpha particles decreases. This may be one of the explanations. So we're talking about local effects, probably. Nobody know, of course, but it looks like a local effect. What do you think? There should be some physics behind your statistics, right? So what you see, if the beta increases, the plasma beta increases, number of alpha particles decreases. High plasma beta is typical for current sheets, and I assure you that in these sheets regions, number of current sheets increases dramatically in comparison with the surrounding solar wind. That's exactly what you see. So these results may be just about current sheets.
I not totally understand you, but
Maria, can you comment on this?
I try to make some comment. Olga, I think that here we concentrate on the anti-correlation for their alpha abundance and beta.
That's exactly my point. The higher beta is, the lower the number.
So, and at the same time, Alexander showed that it's not some large scale one current sheet, but a lot of small scale. current
Exactly.
sheets. Yes, yes, and so you are absolutely right. But I think that we need to look on details about the structure. If it really several current sheets, or it's the part of one. So it's some detailed structure of one current sheet. So it's
No. Inside the sheets, it's impossible to have only one current sheet. Of course, we are talking about many current sheets. And the point is that usually people think that the low level of alpha particles is a feature it characterizes only the heliospheric current sheet. You see?
yes.
This is very important what you are doing. I'm very I'm excited to see your results, actually.
Thank you.
Thank you. Very interesting. So no questions? No more questions. Okay. See you at 4. Thank you very much. The session was great. Thanks to all the speakers. I enjoyed it. I hope the others too. Thank you. See you. Please use the other link. Okay. Bye.
Thank you, everybody. Very interesting.
Okay. See you later.